about thank you very much for that wonderful prayer. And we shall be starting direct. You can first mute now. So I request in this session will be very participative. And as usual, we are going to use the two areas. Number one, we shall be using the chat. And also, we shall be raising up the hand if there is any issue. We shall be beginning direct. And as I had told us, today we want to continue from where we stopped last time. This is our third lesson of Senior 6 series that we've had in 2026. And last time we looked at chemical properties or chemical reactions of alkenes. We looked at a number of them and remained with these three oxidation using potassium permanganate, ozonolysis, and also polymerization. And I promised us that in this session, that's where we shall be looking at hybridization in full. We look at the SP, we look at SP2, we look at SP3 hybridization. And we shall also be seeing how important hybridization is in the organic chemistry. So today, that's what we shall be looking at. And still, it's Nyerimbibi Isaac who will be taking us through today's session. Okay, last time we met, we looked at these chemical reactions. We were able to do the mechanism on addition of hydrogen, which we also called the catalytic hydrogenation. We also looked at halogenation in presence of inert solvent and also in presence of water. Those are two things we looked at. We also looked at addition of halogenic acid. And in addition of halogenic acid, that's where we saw the Markovnikov's and the anti-Markovnikov's rule. Then we also looked at hydration of alkenes. And in hydration of alkenes, that's where we are adding acidified water. That's why we're adding acidified water. Then we left out the three reactions. Reaction with potassium permanganate, which we are calling the oxidation using potassium permanganate. And then we left out polymerization and ozonolysis. Can I see by show of hands how many people did some research about oxidation, polymerization, and ozonolysis? By show of hand, I want one person to take us through the first one, reaction with potassium permanganate. Okay, Samuel. Samuel, unmute. Samuel? Oh, Emmanuel. Yes, Emmanuel.
Good afternoon, sir.
Good afternoon. How are you?
I'm fine. So, reaction with potassium permanganate. There is.
We are going to start with example. Let's look at the example. The one which I gave you. I gave you which one? Which compound? I gave you two compounds. You can take us through the first one. The first one was which compound?
The first one, let me see.
Ethene, yeah?
Yeah.
Ethene.
I think.
And we're reacting it with potassium permanganate. It's ionic form, aqueous. Okay, tell me the product. What is the product here?
So it's going to form.
I want us to move faster.
It's going to form a diol.
A diol. Okay.
Yes.
You read for
So
me
it's
as
going
I
to
write.
be
Mm.
CH
CH.
CH2. It's going to
Yes.
be Then OH on the carbon.
OH like that.
Yes. Then
Okay.
CH2
CH2
OH.
OH. And you're calling this one. What is the name of this compound?
It's called. I'm not
It,
it.
okay. You said it is a diol. You can see it is
Yes.
having two um hydroxyl groups. And you recall this is a functional group for alcohols. Are we there? But now
Yes.
they are two. That's why you're saying now they are diols. You call alcohols, you call them alkanols. They have the last part, the suffix of "ol." But now, because these ones are two, now they become diol. But it's coming from this compound with two carbon atoms, and they have that prefix of ethan. But now, because they are diol, so ethan, where are these OH groups? They are on the first carbon atom and the second carbon atom. So we also give the position of the functional group, carbon 1 and then carbon 2, and then we say diol. So we call it ethan 1,2 diol. Let's go to mechanism very fast. The mechanism. Okay, you're going to take me through this mechanism very, very fast. What do I do? Do you know the mechanism?
Okay. Yes. Let me
Okay.
try.
Yes.
Yes. So we are going to uh, uh, open up the magnesium, the mangan. Sorry,
The manganate.
how is it? Yes, the manganate.
Okay.
So we are going to show the the manganate bonded with oxygen with two double bonds on one side.
Two double bonds.
Yes, and on another side.
Okay.
It
Then
also
on this side.
on the yes two. Then on the other side one and the
Okay.
negative.
And the negative. Good. I
Yes.
like that. Okay, let's continue.
So we are going to bring our ethene.
Then please, other members, focus very well because many people were saying mechanisms are very hard. So today is your time to be keen, and this should end today with because we are getting done with alkenes. So which means any question about alkenes we should be able to respond to it. Okay, move on. What do we do?
So the negative, okay, it's going to attack the carbon atom.
In
This
simple
carbon atom.
terms,
Okay.
do you recall
Yes.
the ones we are saying that they're electron rich and the ones which are not electron rich? But now, do you think this one is going to work? Okay, okay. What were you telling me? What do we do?
Okay. The electron-rich species was going to attack the carbon.
Hmm. To
Then
return. So this
yes,
one, which is negative, it is going to come. It comes
yes,
on the carbon.
carbon, and then also the uh the double bond. One of the electrons are going to be at are going to be attracted. Okay, attacked to the what? To the oxygen.
Okay.
Yeah, like that.
Uh-huh. But
Then
now, when this one comes, what will happen? Will this oxygen remain stable?
no,
Which means this
it's
bond
going
will also do what? Break.
to break. Yes,
So when it breaks, how? Which means it's going to add more on manganese, and also this manganese this bond attached to manganese will say no, I'm not safe. It will also do what? Break.
break.
Like that. Yeah.
Yes.
Okay. So what we form? Let's move on. We
So we
shall
are going to.
form. I believe what we are forming, we are getting it from here. We are still having our CH2. Here we have remained with a single bond. it is attached to CH2 like that. Yeah.
Yes.
Okay. Then this bond block, but is joining to oxygen, meaning we are forming a single bond with the oxygen. Are you seeing that? This one
Yes.
and this carbon atom. But also you call this oxygen is now forming a bond with this carbon atom. So you have oxygen forming a bond with this oxygen atom.
Okay.
Then we have here the
Manganese.
manganese, and here we remain with
Yes.
a single bond. So there's a single bond, and even here we have a single bond.
Bond.
Here we remain with a double
Bond.
bond, and here we have a single bond and oxygen with a charge. Because when this one comes, it remains with a charge. This charge meaning a full, these are two electrons, because this bond, it has a two electron. When it breaks, to bring a charge. So what happens? You recall we have not yet formed our product. Our product is a diol. Maybe for the product, let's use a red, okay?
Then is it there is addition of water, is it?
Where are we
I'm not
getting
no
water?
no. I'm not so sure about the next part, sir. I think you can help me with that.
Okay, you recall in our reactants here, we're having a manganate ion and hydroxide ion. Are you seeing it? So which means
Yes.
what we're going to do is addition of the hydroxide ion here. So when we add hydroxide ion, it is aqueous. So the whole of this manganate will break, and then the hydroxyl groups will attach to repress. So here we shall be having CH2. So the hydroxyl group will attach to these ones, forming our final product. In simple terms, that's how we get our diol. So initially, we are seeing the manganate breaking and then attaching. Then when we add hydroxyl group, this hydroxide, that's when we form our final product. Now, I want another person. Thank you very much. That was Emmanuel, yeah? Can we clap hands
Yes.
for Emmanuel? Let's clap hands for Emmanuel for we have done it very well. Emmanuel has done it very well. Let me have another person. I'm going to put our second item, which I put, then another person can also take us through. We shall be beginning with the product. Which product would we form? And from there, we also go to the mechanism. Who is ready? By show of hand. By show of hand. Good. Joan. Joan?
Good afternoon, sir.
Good afternoon. So, Joan,
I
do you have a question or we're moving on? I give
It's
you part
actually
B.
a question. It's actually a question.
A question, okay.
Yeah, I'm confused with the mechanism because now, okay, on that issue of the hydroxide, okay, the hydroxyl ions coming in, first of all, we saw here the oxygen atoms from that permanganate ion. They
Yes,
joined onto that
to carbon atom. Yeah.
okay, yeah, on the carbon atoms. Now
Yes.
I'm asking myself, how do the oxygen atoms of that permanganate ion, how do they move away? Then the hydroxyl ions come in, or where it's only the H atoms from the hydroxyl ions? Okay, like I'm confused.
So here we are adding hydroxyl group, hydroxide ions, and when we add
Mm,
these hydroxide ions, are the ones which are going to come and repress. So there is oxidation taking place. Only that we are not we're not going to show this other complex mechanism in between here, because this
mm,
other complex mechanism, we don't normally do it right here at A level. At least we do this mechanism from this point. We see how manganese is coming in, and then when we add the hydroxide group, how it breaks off, and then we have the hydroxyl, that diol. So this complex other mechanism here is the one we don't normally show. But we shall look at it at another level also. When we, the good thing most of us who have continued with chemistry at university, you will be looking at it in that organic chemistry for university. We shall look at it there at another level. But for this level, we just end at this mechanism at this level, at that. But when we move on, we can be able to see how these ones are, this manganese is breaking off, and then we have this dipole. So that is where we end at when we look at this mechanism. Because at O level, we just look at the product. At A level, now we look at this breakdown, this mechanism, how it comes about. Then on higher studies, we can also look at how this one comes in and how this one breaks off.
Okay, thank you,
But
sir.
Joan, you remain on the phone. You're not going to go without answering this part B. I don't know whether you tried out part B.
Part B. Okay, I'm just kind of like joined in, but okay.
No, part B, I left it last time we met on Monday.
Oh, last day. Okay, let me try.
Last time you were not there?
I actually didn't attend the entire lesson because I was busy.
Okay. But a good thing you have attended today's lesson. Which product can we get here? And before you get the product, what is the name of this reactant here? What is the name of this alkene?
That's a cyclohexene.
Cyclohexene.
Hexene.
So which product do we get?
The name is kind of going to be disturbing, but we
Okay.
have
Which
the
product
product.
we get?
It's going to be okay. We are going to have something. Okay, we are going to have hydroxyl groups on the carbon atoms that had the double bond.
Okay, the carbon atom that have double bond. So this is a carbon atom number one. This is a second carbon atom. So the
Yes,
carbon atoms with the double bond are the ones which are going to have the hydroxyl
hydroxyl.
groups like
Yeah,
that. Yeah.
then we form a diol. Yes.
Diol. Which diol is this? So the name of this diol.
Mm, I actually don't know.
Okay. Thank you, but good thing you have tried. Who can tell us the name and the mechanism? We move on faster. By 3, we should be done with these mechanisms and we go to hybridization. Who is ready to tell us the name of that compound? Oh, no one is ready. We can copy from what we have done already. Let's look at this. From ethene, we got ethane 1,2-diol. Now, what do we get? Yes, Prosper. Hey, it is Prosper? Okay, Prosper and Emmanuel. Prosper?
Good afternoon, everybody.
Good afternoon.
The name of the compound is cyclohex-1,2-dio.
Hexe.
One,
Oh,
two.
okay.
Yes.
You see, ethane. So which means we are going to say hexane.
Hexane.
Hexane. Okay.
1,2-dio.
1,2-diol.
Oh.
Very good. Thank you. Do you think you can take us through the mechanism?
Okay, so let me try.
Yes, good. Mechanism.
So that cyclohexene, we are going to see form the bonds of the magnesium. I mean, of the permanganate of the manganese.
The manganese. So let me. The manganate.
Yes.
We distribute. So this time round, since this side, maybe we can rearrange our oxygen atoms like this. And you recall we had all of them double, then we had only one with a negative single bond like that. Yeah.
Yeah. So as we know that if electrons move from where the electron rich to electron deficient.
Yes.
So electrons are going to move from that oxygen with the negative, which is electron rich, and they're going to attack on atom number 1.
Okay.
So that double bond in the cyclohexene will also attack the oxygen atom down that of magnesium. Yes.
Good.
So then that bond will break and gives it to that manganese. So as it breaks to the manganese, also that bond up of the manganese will also break and give to oxygen to make it have many electrons, and it will gain a negative.
Good. So which means our product will be this one. You recall now that double bond has disappeared. Yeah.
Yes.
It no longer has a double bond, but there's a bond created between this carbon and oxygen. Then there's a bond formed between carbon 2 and
number
this
2 oxygen.
Then we have the manganese. Then it is attached to this single, and it's also attached to this single. Here we still have a double. Here we have a single with a negative charge. Then, so what will be our next step?
We are going to add the hydroxyl, because we had in our reaction permanganate and the manganese and hydroxyl group. So we're going to add the hydroxyl, which is aqueous, and then the manganese will disappear. Then we shall form cyclohexane 1,2 diol.
So we shall form our product, cyclohexane 1,2 diol. Very good. Can we clap hands for him? Thank you very much for leading us in that. I believe now, if we are to talk about anything about oxidation or reaction with permanganate or potassium permanganate, I believe we are able to do that number very well. So when you retreat, maybe just going back, just a simple highlight and we move on. We are saying that reaction with, there's an error here, we are supposed to have H. We are saying that reaction with potassium permanganate, in this reaction, we react alkenes with acidified or alkaline potassium permanganate. So these are ions just. So we are saying that we can use acidified or alkaline. So here it is alkaline potassium permanganate. Are we there? We can also use either acidified or alkaline. So we have used alkaline here, potassium permanganate, and we are saying that when we do that, we form diols at room temperature. And what is the observation? The observation is that the purple color of permanganate will turn to colorless. So when you look, initially, this permanganate it is purple. So when the reaction takes place to form a diol, it changes to colorless. So the purple color changes to colorless. And this reaction is used for testing for unsaturation. This is a reaction that we can use to test for unsaturation. If we have two compounds, like ethene and ethane, and you want to know which one, maybe this one is A, compound A, and this is compound B. Of course, you don't know whether this one is an alkene or whether A is an alkene or B is an alkene. So if you don't know and you want to test that two, which one is an alkene and the other one is not, we can use addition of potassium permanganate. When you add potassium permanganate to A, it will change from purple to colorless. But if you add it to B, which is an alkane, it will have no change. So we are saying we can use this reaction to test for unsaturation, to know which one is circulated and which one is not circulated. For uncirculated compounds like alkenes or alkynes, it will form such. It will change from purple to colorless. Anyone with a question, or we move on? If you have a question, you raise up. Bettina. Yes, Bettina?
Sir, good afternoon, sir.
Good
For me,
afternoon.
my question there with the testing. So do we
Testing,
get
yes.
the same observation for testing when we're using acidified potassium permanganate and when we're using alkaline?
We get the same products. Like as I said, alkenes react with acidified or alkaline potassium permanganate to form diols at room temperature.
Such other queries about the testing, like you've said, if it is acidified potassium permanganate solution and it is heated with an alkene, we're going to get the purple solution turning colorless. And then does it swim for alkaline? Because someone was like telling me it turns from purple solution, it turns to green. So is that true?
For which one? When you're testing on which one?
For saturation, and then you're using alkaline potassium permanganate. Does it turn green?
When you're using potassium permanganate, when it is
Alkaline.
acidified and when it is alkaline.
Yes.
Oh, so you're asking which color does it form? Okay, you remain on the call. Joan is answering. Joan, you unmute.
Well, actually, I'm not kind of like answering, but I also have the same complaint, because now in the chat they told me that demystifying chem is a pamphlet. So it was the one I was actually using, and at school they also told us that when they use alkaline potassium permanganate, we get some observation that is red dark green, something like that is dark green. Then with acidified we get colorless. We observe a colorless solution. Then I saw this in this demystifying, they were like the alkene for it when it reacts with acidified potassium permanganate, you get a carboxylic acid, but then with alkaline potassium permanganate, you get a diol, just like we have done. So now I'm also like totally confused. Because even the same book was saying, Boba, the naming, they were like, now for example we have ethan 1,2-diol. Then that book, that pamphlet was like, if you're naming alcohols it's more than one hydroxyl group, they call them polyhydric something alcohols. They say you're supposed to leave the E at the end and it feels like ethane 1,2-diol. Now I'm confused with all those three, the naming and also the color changes while testing, because for us they told us that with alkaline potassium permanganate we get a dark green. We observe from purple solution it turns to dark green. Then with acidified, from purple it turns to colorless. And with acidified that we don't get a diol, we get a carboxylic acid. Now I'm confused.
Okay, thank you. You keep on. Let's have Alan, Kalen, Doreen. You remain on. We clear that and then we can move on. Yeah. So that by the time we leave this, we are all okay. Yes.
Sir,
Good afternoon. How are you?
I'm fine. Sir, I also have a query on that part of, aren't you said we can either use acidified potassium permanganate or alkaline potassium permanganate. So do they, yes?
Yes, I'm getting.
So do the two solutions give out hydroxyl ions, even the acidified potassium permanganate?
Okay. So for you asking, do they all give us diols if we use potassium permanganate, alkaline, and when we use acidified, yeah?
No, like as in the ions, they all give hydroxyl ions, even the acidified one.
No, acidified, when we are doing acidified, it is represented by hydrogen ions. While alkaline
Yes.
is represented by hydroxyl ions, like the one we have done. Yeah?
Yes.
So for
But then how does
alkaline,
it
yes?
But then how does the diol come about when you use the acidified potassium permanganate?
Now, don't you worry. Let's look at that here. Let me hope we are all there. Let me first remove polymerization, and then we can look at using the acidified potassium permanganate, or we can just talk about it here. So when we use acidified potassium permanganate, are we there? Let me hope we are all getting. So we are saying that this reaction of potassium permanganate can be used as a test for saturation, to know which one is circulated and which one is not circulated. Now, when you use potassium permanganate alkaline potassium permanganate, we are seeing that we are getting a diol. And now the question is, what about if we use acidified potassium permanganate? What do we get? For example, maybe we can use another color for difference, and maybe let's use this. Let's use this example. Maybe we still have ethane. And then if you say acidified potassium permanganate, meaning we are going to have potassium permanganate acidified. Acidified will be represented by hydrogen ions. I believe you still have 3 people who have microphones unmuted: Bettina, Joan, and Doreen. So we're saying that for this case with acidified, we are not getting a diol. Instead, we are getting a carbonyl compound or a carboxylic acid. We can get 2 products, but depending which, if it is a strong oxidation or if it is weak. The more you do the oxidation, the higher the oxidation, then we get the carboxylic acid. But less oxidation, we just get a carbonyl group. You recall we have carbonyl groups. We have aldehyde and we have a ketone. We shall look at that in our next series as we look at senior 6 work. I believe that will be for the preceding sessions. This is our last lesson for organic. Then we can go again to maybe physical and inorganic. But our next lesson will be for physical. So what are we saying here? We are saying that when we are using acidified potassium permanganate, we get a carboxylic acid for strong oxidation. But if it is not strong oxidation, initially we can have carbonyl group which can still be oxidized to a carboxylic acid. So which color changes do take place here? So you find out that when we do this, because potassium permanganate, you see to be changing from purple note to colorless as it was for alkaline, it will be going maybe to orange, sometimes depending on which color, or depending on which oxidation, whether it's strong or weak. But the colors can range from green or orange in there. So depending which one that we are having in that case. But I want to hear from us. Do we still have a query on potassium permanganate acidified and potassium permanganate alkaline?
I think I've been cleared a bit. So meaning that what you're saying is that when I use the alkaline potassium permanganate, my product will be a diol. And then when I use acidified potassium permanganate, my product will be at higher oxidation, my product will be carboxylic acid, and low oxidation, my product will be a carbonyl group.
Yes. Now, which carboxylic acid do we get? For example, here, you see, here, which means you're going to get methanoic acid and carbon dioxide gas, terminal alkenes, yeah? I don't know, I believe you know terminal alkenes. For example, if you have even a propene, CH double bond CH2, which means in this case, strong oxidation shall be having ethanoic acid and carbon dioxide gas, which means here we shall be having methanoic acid and carbon dioxide gas. Are you getting that?
Yes.
Yeah, so I believe now it is clear. But what are we saying? This one does not work for alkanes which are circulated. So, which means we are saying that this reaction or these reactions with potassium permanganate can be used for testing for unsaturation. Because with these ones which are uncirculated, there is a change. While for circulated, there is no change that will be observed. Are we clear there? Maybe let's hear
Yes.
from Edith Mbuga. Edith Mbuga, you unmute and then you can move on. Edith Mbuga. Yes, please.
Yes, good afternoon.
Good afternoon.
So me, according to my research,
Yes.
I have made this conclusion that we
Okay.
are having an alkene.
An alkene, yes.
Yes, and we are trying to test if there is a presence of a double bond. So
Yes.
when you use alkaline, according to my observation, they said the
Yes.
solution is purple color fades, and a
Changes to
brown,
colorless.
yes, changes to colorless, and a brown precipitate of, because other products are being formed, so we form magnesium dioxide in the alkaline. So there is another color that is formed
Mm.
for alkaline, but
Mm.
in the acidified,
Yes.
I'm, I'm observing that only there's the fading of color.
In a acidified, there is only fading of
Color, because we have formed only the carbonyl compound and other products like carbon dioxide and water, which won't affect the color. But in alkaline, we have formed magnesium dioxide, which changes the color to brown because the color is affected by magnesium dioxide.
Okay, good. Let me hear from Sylvia. You keep there. Yes, Mbuga, that is good. First, keep there. I hear. Sylvia, what are you saying? Are you concluding with what Mbuga is saying? Sylvia? Yes, Sylvia, you had something. Sylvia, let's move faster. Okay, Prosper. Prosper, you unmute. I want us to end this at that, and then we can move on.
So, sir, as we are taught,
Yes.
that when alkenes are treated with oxidizing agent like dilute alkyl potassium permanganate at low
Is that Prosper?
temperatures,
Yes, Prosper. Yes.
a hydroxide is added to a carbon with a double bond, and the purple solution of potassium permanganate turns green during the reaction, and hence this reaction is used to test for unsaturation in the molecules, as you have
It
said.
first wait. Turns to green when we add an alkaline.
Yes.
Which green product is that? Now, when we are doing all this, let us.
Yes.
I liked what Mbuga said. Mbuga, edit. Let me hope you're still there. Mbuga.
Yeah. Yes,
Yeah,
sir.
I like what Mbuga said. From what we are observing here, maybe we first mute because the sounds are now becoming nice. Let me mute all of us that we can hear. Okay. Let it be clear, the good thing we have had our submissions. So what he was telling us that there is orange, but where is the orange coming from? Now here, the good thing we have all the products for acidified and for alkali. Now for alkali, we see that we are forming a product, a diol, and Mbuga told us that actually when this diol is formed, there is this manganate group which has disappeared, which is coming also this side in which is forming the precipitate which is brown, or some people call it orange precipitate with alkaline, but of course that purple color is still changing in when we are forming this diol. Now when we come to acidified, we see that we are forming only this acid and carbon dioxide gas. the acid and the carboxylic acid and the carbon dioxide gas. So we can conclude and say that with acidified potassium permanganate, it is changing from purple to colorless. While in this side, it is changing from purple to maybe a brown precipitate. Now, in order to acidify and alkaline, there is a change that is being observed. Only that one side we are forming a diol for alkaline, while this side for acidified we are forming a carboxylic acid with strong oxidation. So, which means we can use this method or this reaction for testing for the anion circulation. I want to see whether we still have a hand up and then we can move on. Anyone with a question or we move on? Good. We can use the signs to show that we are moving on. Okay, Audrey, and then we move on. Others, let's put in the chat. Audrey.
Good evening.
Good afternoon.
Oh, okay. Good afternoon. I'm sorry to take you a little back, but I'm requesting for how the breakage of the potassium permanganate occurs, because
Where?
okay, I'm kind of lost on how you do it.
On which stage?
The first one, because you said that the oxygen ion is going to bind to the carbon, hence the double bond binding to the
Breaking.
oxygen with the double bond. Then okay, I am a bit lost. I can't really see how to explain it.
Oh, so we are saying these extra electrons on this oxygen are going to, because they are electron rich, they are going to come, they will attack this carbon atom. So when they attack this carbon atom, you recall when this one attacks, are you still on?
Yes,
when it
teacher.
attacks this carbon atom remains unstable because now it will be having extra bonds. Because a carbon atom is supposed to have a maximum of 4. So when it has less or above, it will be unstable. So when this one comes, it will be bringing extra. That's why this bond, these electrons for the pi bond are the ones which are going now to break because they are weak. They can easily be blocking very fast. So these ones are going to break. So they'll break coming to this oxygen because when they come to this oxygen, but now this oxygen can accommodate a maximum of only 2 bonds. So which means also it will become unstable. That's why this bond will also break, bringing to manganese. But now manganese will also be having excess. That's why this one will also break and then stabilizing the compound. So when you stabilize this compound, it will leave this negative charge on this oxygen atom. So that's how it moves on. And that's how we also did for our second part, the same case on our second part, where we are looking at just a cyclohexene. Okay, thank you. Thank you, Audrey, for that. Maybe, Audrey, you can take us through polymerization, just the example I left you with, and then we can move on. Polymerization.
Teacher, I'm actually joining for my first time, but I can actually, I know how the things work, but I didn't get the question that you had left.
Oh, it's okay. So for polymerization, I had left this for an alkene. When an alkene undergoes polymerization, a number of them. So we put N. We had put N to show that a number of alkene undergoing this polymerization process, and I had given the conditions with presence of oxygen catalyst at high temperatures, and also high pressure. Which product do we get when polymerization takes place? Maybe to just give you a simple introduction on polymerization, I believe we all know that, because the reason why I normally do this is because I know we have these notes for these chemical properties. So we are just trying to practice, yeah? So we say that in this reaction, polymerization, in this reaction, this is where very many simple molecules combine to form one long chain molecule. I believe that is the definition of polymerization, where you have small molecules, the ones we call monomers, combining to form a bigger long chain molecule, the one we call a polymer. And that's the one we call polymerization. In simple terms, our monomer is this ethene. So which means ethene is going to combine with a number of them to form our polymer. So in simple terms, I'm asking, which polymer are we forming? Audrey, which polymer do we form?
I think you're forming polyethane.
Polyethene.
Ethene.
Do you know how we can write it? Its structure?
Yes,
Okay,
yes.
tell me.
You do, there are some big box brackets.
Like this.
No, they're not that curved, but they're longer.
It's okay.
Okay, then you expose the carbon, then you put a long line with its no.
Like this. We extend these
No,
ones.
you don't put the H2.
Oh, what do we
Like,
put?
okay, for us we studied that it's actually you're exposing the branches. Then after, but
Expose.
it's still the same thing. It's still the same thing.
So
So
can
then
I
you're
leave it
going to
like
put
that?
an end. Yes. Then you put an end behind on the
And
last branch.
somewhere on this one.
Yes.
Okay. So I think that is almost the same as what? Now, do you know how it comes about, the mechanism?
Our teacher told us that the mechanism was not really needed. We just get it like that.
It is not really needed. Very good. But we can have a visualization of how it occurs. Just in simple terms, let's look at this. Just we're going to give a sample of like 2. Because you recall, the reason why I told you it may not be necessary, because you see this N is representing very many of them, isn't it? Very many of ethene molecules. Are we seeing that? So
Yeah.
maybe even what I'm going to show you is not a real mechanism that it's the one we are supposed to use, but I want us to see where this one comes from. Are you seeing that?
Yeah.
Now, so we are having ethene molecule here, CH2 double bond, CH2. Maybe let's use like 2 of CH2, CH2. Let's use like 3 of them, CH2, CH2. These are 3. But of course, here you're saying that there are many ethene molecules. So what happens, this double bond, because there are free electrons here for the pi bond, this bond is breaking, it comes to attack this carbon atom of the next alkene molecule, this ethene. But it attacks the carbon atom with the double bond. Now, when it attacks it, this carbon will become unstable, and then this bond also will break, goes to the next carbon atom of another molecule. So the system will continue. This one, when it attacks this carbon atom, this one will be unstable, so it will do the same. It attacks the next, but now the next is not there. So what is happening? The product, I wanted to visualize where this one comes from. So the product will be, you recall here we are having CH2. Now we remain with a single bond, CH2. Now this one, it broke from here, it came to form a bond with this carbon atom. So there is a bond which is being formed between that and now this one. CH2, single bond, CH2. Now this one came to form another bond with this carbon atom. So there is another single bond, CH2, single, CH2. Now it continues. This one was going to form another bond this side. So it continues. But also, this one is not, this one could be attached with another one from this side behind. That's why you normally put another dash. because this carbon atom is not stable, it is having only 2, 3. So we put another one to show that it is attached to another carbon atom. So when you're writing that there are very many ethene molecules, we can just come and choose, maybe we say, let's consider only this. We consider here. Then we break off all these ones, and then we put our N here. These ones, we break them off. These ones are breaking them off. But that this bond here is showing us that there are more ethene molecules attached to this. Even this side, this one is showing that there are more ethene molecules attached on the other side. Audrey, is it somehow clear?
Yes, teacher. Teacher, the conditions you use, that's oxygen catalyst at those temperatures. There's another book that uses titanium tetrachloride in the presence of triethyl aluminum catalyst. Then, and there are others that use phosphonic acid in the presence of an inert support at moderate temperature. So, can you clarify on that reaction?
Now let me show you this one. We can also have this one. Before the analysis, can you allow me to cancel this first? And then maybe I give you another example that we can have other conditions. Like, let me use, which name is given to this? What is the name of this alkene?
Propene.
Propene. So we can also use ethyl oxide, and we heat. We still do get our polymer. So there are different conditions we can use to do our polymerization. So I've used that one. We also have this one, peroxide and heat. You have also told me yours, which tetra, you said it is called what?
Titanium tetrachloride in the presence of triethyl aluminum catalyst.
Triethyl aluminum
catalyst at
catalyst.
50. Yes. Now, like for peroxide, for the propene, you're going to use it at 10 atmospheres and at 100 degrees Celsius.
So you can see that we can have different books having different conditions, but they are giving us the same product. So have you gotten also the one which is having a peroxide in presence of heat?
The peroxide?
Yes.
No, I've never encountered it, but I know the product is what? Polypropane.
Hey, here,
propane. I don't know why that.
Not propane, it becomes polypropene because this is propene. So when you're forming the product, it becomes now polypropene. Are you getting? Even this side, it was polyethene, not ethane, because our initial, it was ethane. So it combined a number of ethene molecules to form polyethene. And now, let us see, how do we get this product? You recall the bonds are between where they are a double bond. This is where we have, this is CH, single bond, then CH2. Now, which means this carbon atom is going to bond with other propene molecules. So there we put a dash. Then this carbon atom here is the one which is attached to other propene molecules. And then this is a branch now. This becomes a branch here, CH3. And then we have our product. Have you seen how I've gotten my product, the polypropene?
Yes, teacher.
Yeah, I believe it is clear. And even if I give you this, let me show you now this. But2 in. I know Audrey is on call, but any other person should be seeing what you're doing and you also follow. If you have a question, you can ask. This is a beauty 2 in, isn't it? So since it is beauty 2 in, which means if we use peroxide, if you use a peroxide and we have our heat here, meaning this single bond, this one, it is between these double bonds. So which means we are going to have CH, Audrey, the hope you're seeing.
Yes.
Between here, we have a single bond because the other one is going to form a double bond between this carbon atom. So we have a CH. Now this CH3 becomes a blanch. Even this one becomes a what? A blanch. And then this one is going to attach to another butene molecule. Then even this bond is going to break to attach to another butene there. And then this one, we call it a polybutene. Is it clear?
Yes, teacher.
Okay, thank you. Let's run to
Teacher,
ozonolysis.
an inquiry.
Yes, please.
Still on the conditions. Will the conditions be given to us, or we must grasp all the conditions? Like,
So you don't need
if
to,
we
you
react
don't
with
need to, you may not need to grasp all of them. Instead, you need to know during polymerization, which conditions am I versed with? Which condition can I use to do my polymerization reaction? So you may be knowing the peroxide and you heat and you get your product. You can be knowing oxygen catalyst at high temperature, high pressure, and you get your product. What you need to know is which product do I get during polymerization and which reagents can I use. The good thing, all the reagents are giving us the same product. So you don't need to cram this one. Understand which product we get, how do we get it, and then you can get some reagents you can know that they give us which product, the products. So you can know this one. You already told me the one you know, and now I've introduced you to peroxide with heat. I've told you the one for oxygen catalyst, high temperature and high pressure.
Thank you, teacher.
Okay, I want us to run very fast. This is our last part, ozonolysis. Did you look at ozonolysis, Audrey? Jackson? Unmute, Jackson. Yes, Jackson?
Teacher, my question was, why do they branch the methyl groups?
Oh, very good question. Why do they blanch the methyl groups? To answer you, before I answer you, Jackson, can I give you only this one last example, Jackson? Yeah? I have NCH3, Jackson.
Yes.
CH, H2. I have a peroxide and I have heat. Which product do you think I'll get? So Jackson, to move on,
Yes.
look at this. If you looked at how I was doing the mechanism, this double bond here is the one which breaks and goes to join another monomer. Are we there? And when
Yes.
even another monomer is coming, it attacks the carbon atom, which is close to the double bond. So these are the points of interest we are looking at, these carbon atoms, carbon 1 and this carbon 2. Are we there? So when this bond breaks, it is going to attach another molecule. And also when another molecule is coming, bringing its bond, it is going to attack this carbon atom. So everything is between the double bond, where the double bond wants CH, but you recall now when the polymerization takes place, we no longer have the double bond, we remain with a single bond because the other double bond is the one which helped in attaching this carbon atom to another molecule. This is 2. So this is the bond which blocked from here and went to attach to another molecule. Are you seeing that? Now, this one is going to remain as a blanch. What is going to be a blanch? It is CH2, CH3 now, the whole of this. So here we have a dash, and then we put this. Have you seen now how it is going to look like now?
Yes, teacher.
So it's not a must that it's a methyl group which becomes a blanche. It depends on the compound. Jackson, are we clear?
Yeah, thank you very much.
Okay, welcome. I see time is running, but we are on track. Let's do ozonolysis. And what do you know about ozonolysis, Jackson?
According to me, the addition of oxygen.
Which oxygen? You recall the word is ozonolysis. Jackson, I want you to, can I have another person raise up the hand so that I work with Jackson and maybe another person? We move to with two people. Yes, Angel. Angel, unmute. So we're going to move two people, Jackson and Angel. Okay. Angel, what do you know about, so Jackson was telling us adding oxygen. Okay, Angel, what do you say about that? Angel? For example, we have our ethene. We want to do the ozonolysis. Which reagents do we put? Which reagents? Jackson?
Yes.
Which reagents? Okay. Jackson, let's work with, Mariam has gone off. Let's work with Ruth Namakula. Ruth, unmute. Yes, Ruth.
It's about ozonolysis that
Yes.
alkenes react with ozone.
First stop there. Ozonolysis is coming from the word ozone. So we're adding ozone in the presence of what?
In presence of how do they call it? Carbon tetra meth. Yes, carbon tetramethane or tetrachloromethane.
Okay, carbon tetrachloride. Yeah?
Chloride, yes. Sorry.
What do we form?
So we form an aldehyde. The terminal bonds form an aldehyde.
Do we form aldehyde immediately?
Okay, they react with ozone to form ozonide, which on hydrolysis which on hydrolysis generates carbonyl compounds.
Generates carbonyl compounds. I like that. So, in simple terms, during ozonolysis, we are adding ozone in the presence of carbon tetrachloride to form ozonide. And then on hydrolysis, we form aldehydes. And if the aldehydes can be a ketone or what? A ketone or what?
Or an aldehyde.
Sorry. So we form a ketone and
we form
aldehyde.
carbonyl compounds, for example, aldehydes or ketones.
Very good, thank you. We form carbonyl compounds. And these carbonyl compounds, they can be an aldehyde or a ketone. Good. So, which reagent do we put here on hydrolysis here? What do we add?
Water and zinc.
Water and zinc. So we can add zinc and water, and then we just warm it, yeah, to form an aldehyde. Ozonide. So do you think you can tell me how we form this ozonide here?
The mechanism.
Not necessarily mechanism, but the compound. Yes.
The compound is
the mechanism.
HCOH.
Okay, C.
HCOH. Something like that.
I want us to draw the structure. Anyway, you recall we're adding this one, ozone, which are 3 oxygen atoms, isn't it?
Yes.
And we are adding it, we add it where the double bond is. So, which means between the double bond, we have a CH2 and a CH2. Are you seeing that? So
Yes.
we're adding this O3 between these two, where the double bond is in here. So what happens? We are going to have one oxygen atom down up there, then the oxygen molecule, the 2 oxygen atoms will come down there. So at the end of it all, you see that there are 1, 2, 3 oxygen atoms which form our ozone. And now this is our ozonide. But how are we forming it? I wanted us to look at that criteria. Anyway, I'm going to put part B and also see how we can form its ozonide compound so that we can view it very well. That even if it is any other compound, we can be able to derive and also get to know our products. Are you seeing? So which products do you think we can form here on hydrolysis? If you add zinc in the presence of water, and water in presence of zinc, and then we warm. Which products do you think we are going to form?
The aldehyde now.
So which means we're going to form only aldehyde. That time, most of the time we get aldehyde when we have such terminal, because for ethene, it is only one carbon atom on one side and one carbon on the other side. And for a ketone, to form a ketone, we are having that carbonyl group in between 2 carbon atoms, and only 1 carbon atom can never form such. So for terminal compounds, they will always form the aldehyde. So which means we're going to form 2 aldehydes, and that is the methanol group, and also this one will form another methanol group, So all these are methanol compounds. All these are aldehyde. These are aldehydes and methanol. This is a methanol, and also the other one is a methanol. But now I want to put different compounds, and you tell me the products. Yeah?
Yes.
Okay, part B. Let's talk about this one. CH3, CH3, double bond, CH3. Then which ozonide compound do we form here? Which ozonide?
So I don't know how to name them, but
No, the names, no. I just need structures.
The structure. So we'll have 3 on this side and there are 2 on the other. Okay, so we try to introduce the oxygen in between. So is it mandatory for it to make a pentagonal shape?
Yeah, because at the end of it, all, we want to have, like, to form that shape in this manner. It will form that such a shape in that manner, one way or the other. Otherwise, when we distort it, because you call it as 1, 2, 3, 4, 5. You get? Because it's like having 5 carbon, and they are in a circular, they are cyclic. So because this ozonide is in a cyclic format, that's why and a 5-sided figure is what? A pentagon. So that's why we normally form that pentagonal shape, that it has that shape which you can easily identify with.
Okay, so I'm going to try, but so that carbon that's near the second carbon atom near the double bond is one that's going to be close to the oxygen atom, both those 2 carbon atoms. So I think they'll be on 2 opposite sides.
Okay, so this
So
carbon
then,
atom here,
yes, that one.
this carbon atom is this one. So it's the one, in simple terms, that these carbon atoms which are having the double bond are the ones you first put here, like this.
Yes.
Then they are the ones which attach to oxygen. First do that. First do that. After doing this, attach all other things on them, which were there. So this one is attached to a hydrogen. Actually, you can even say a hydrogen and a CH3. Are you seeing? Then this
Yes.
one is attached to two methyl groups, a methyl group and also a methyl group. Have you seen?
Yes, teacher.
Then when we put in zinc and water and warm, which products are we going to form?
We're going to form if it was butanol.
We are going to form
Butanol.
butanol. Butanol, that means it has 4 carbon atoms. Now, this is what I want everyone to observe. You look at this side. You recall when we add water, this one is going to form its own compound. This one forms like the way we saw. This one is forming its own compound, and even this one is forming its own compound. So now look at this. In between here, there is a carbon, and then this carbon is attached to oxygen atoms. So this carbon atom is the one which attains the double bond of oxygen. Then these ones are the hydrogen atoms that were attached to it. I want us to focus on this. Are you seeing? This hydrogen and this one are the ones which were there before. But when hydrolysis took place, these two bonds, it became a double bond attached to oxygen. Have you seen?
Yes.
So in simple terms, what is happening? These carbon atoms that were attached to double bond, what is happening to them is just attaining a double bond with oxygen. Only that. What remains on it is what was there. I don't know whether
So we have propanol and ethanol.
Good. Very nice. Propanol, not propanol. It is proper, because we are writing CH3, then C. Now, this carbon atom is the one which is attaining the double bond and oxygen. Then it has another CH3 plus. Are you seeing? Plus. We are having, maybe let me use this one. We are having this carbon atom here, which is attaining a double bond with oxygen, and then it has a CH3, and then it has an H. So this one becomes ethanol, and then this one becomes
propanol.
Propanol. Is it clear now?
Yes, teacher.
Okay, thank you. That is nice. Okay, let's have another person. Who was that? Okay, you have taken us through very well. Having Grace. Grace, unmute.
I just have a slight question.
Yes, please.
Yeah, like on the conditions, don't we require less than 20 degrees Celsius?
No, when you just say warm, it doesn't, when you're warming, it already shows that you're using little temperature. Yeah?
Okay.
So you may not need that. If you already said that warm. If you wanted beyond that, we could have said heat.
Okay.
Now look at
Thank
this. Look at this. I'm the one, I'm still on you, please. Grace. Grace.
Yes.
This time now, I don't want you to give me Sorry, I've made a mistake here. I want to give you another. I don't want you to give me the ozonide. This time round, I want you to. I've combined the two stages. You're saying I'm having this reagent number 1 and this reagent number 2. They're all there. So I want you to give me the carbonyl groups, compounds that we are going to form on this compound. This is our compound. Which products we get?
I'm going to have 2 products. Then I'll have a methanol plus an ethanol.
Where are you getting them? And how? We are going to work with Samsung. Samsung and mute. Samsung and Florence. Samsung and Florence. If you don't unmute very fast, we shall have Linda. Okay, Samsung is okay. And Linda, Naruyinda is there. Naruyinda, Samsung. Who is the first one to ask?
Yeah, Master, my question is how do I know that right now I'm to get a ketone and when to get an aldehyde?
Very good.
Yes,
now,
because it is kind of confusing on when to get a ketone and when to get an aldehyde.
Today, we're going to, I don't want you to go when you're confused. By end of this, you should be, now, you look at this. Look at this. Are you seeing this? Have you understood how these ozonide groups are coming about?
Yes, sir.
Now, after the ozonide groups, are you seeing how we are getting our final product? That our final products, what is happening, just these carbon atoms which had double bonds are attaining a double bond with oxygen. Then other things which are attached to them, they remain. Have you seen? You see, this hydrogen and this one are the ones which were there before. What has happened to this carbon atom is attaining a double bond.
Double bond.
That's why today, now look at this. Can we do the same on this compound? Yeah? Now, are you seeing these carbon atoms? There is this carbon atom. Maybe I change the color so that we see very well. There's this carbon atom and this carbon atom, which are attached to double bond. Are we there?
Yes, sir.
This time around, we don't need the ozonide group. We are coming direct to the product because we have put all the reagents.
Yes.
And what we said is that these carbon atoms are on the double bond. What we do, go to those carbon atoms and give them a double bond with O.
With oxygen.
Yes. Then what happens? The remaining things attach them to it. What remains is C. On this side we have?
It is CH3.
CH3. Then this side we have?
Also CH3.
CH3. The compound is done. Is that an aldehyde or a ketone?
An aldehyde.
Why?
Oh, it's a ketone.
It is a ketone. Have you seen?
Yes.
Go on this side, another product. Do we do the same? This carbon atom, we give it a double bond with oxygen, then we attach the other compounds remaining. So we attach here, it is CH3 still. Oh, this one is the same. Yeah?
Yeah, that one.
Are you seeing that it is giving us the same products?
Yes.
Now, do you think it can maybe just for practice, yeah? For practice, let's try out this. CH3CH double bond CH CH2. Then we have CH3 CH2 CH dash CH2. Let's get the products. We have ozone in presence of carbon tetrachloride, and then we are adding zinc in presence of water. Water, and we are warming. Okay. Then here we have oxygen, CCl4, zinc, water, and we want product. What do we get? What do we get here? We do the same. Come on this carbon atom. Yes?
And
Are you
give it
seeing?
a double bond with oxygen.
Double bond and oxygen. Attach the remaining things. It is H, and then here it is CH3 plus. Do the same. Come to it, give it O. Here you get H, and then here we get H. Have you seen?
Yes.
What name do we give to this compound?
That one is ethanol.
Ethanol. This one is?
Methanol.
Methanol. Are they aldehydes or ketones?
They are ketones.
They are?
They are ketones.
They are?
Ketones.
No, ketones, and you recall the ones we had here. This was a ketone. Is it the same as the other one? This one was these ones were ketones. Are you seeing? And the name given to this is propanone. Even this one is propanone. Are you seeing the difference between ketone and aldehyde? For ketones, they have this double bond oxygen carbon with a carbonyl group in between the carbon atoms. While the aldehydes, they are terminal. You get, so these ones become the aldehydes. Are you getting?
Oh, yeah, yes, now I understand. Thank you, sir.
Now, in your practice time, try this and get for me the answers. Are we there? Then, for practice also, this is the question which I gave you to try, but I'm now very I'm very sure now that each one of us can be able to respond to this item, this scenario item. You can take a screenshot for now, then you're going to try it out immediately after here, because it is application of what we have learned, the reactions and mechanisms of what we have learned. What I need is you to take a screenshot now, try it out, and then you'll be sharing your responses maybe in the group.
Excuse me, teacher.
Jackson, yes, please.
Sir, I was requesting you just help me and pardon on how you differentiate between an aldehyde and ketone.
Okay. Keep alert. Keep alert. Just have a look. So in simple terms, when you talk about a ketone and aldehyde, all these are called carbonyl groups, carbonyl compounds. And carbonyl compounds have what you call a carbonyl group as a functional group. Are we there?
Yes.
Now, for ketones, this group, carbonyl group, is between other alkyl groups. While for aldehydes, this group is always on the end, and then you have alkyl group this side. Is that one clear?
Yeah, thank you, teacher.
Yeah, you're welcome. Okay, so we are going to hybridization, our long-waited part. You know, very many people were asking me, when are we doing hybridization? I know time may not be enough because we have 30 minutes and I'm going to utilize only 30 minutes. What I don't normally do is extending. So I'm not going to extend. And if time goes when I've just covered only one type of hybridization, the remaining ones are yours. Because what I want is to understand. When you have understood, then these things you can do them with ease. Are we there? And when you talk about hybridization, of course, we can't go without talking about bonding. So we are going to first look at bonding in organic compounds. Who can tell us which type of bonding do we find in organic compounds? By show of hands, the type of bonding found in organic compounds. By show of hands. Yes, Gilbert. Gilbert, where are you? Let me see, Gilbert. Yes, Gilbert. Which type of bonding?
Most of the organic compounds have covalent bonding.
Very good. Can you clap hands for Gilbert? They all have covalent bonding. Okay, good. So they have covalent bonding, but you find out that during the bonding, most of the organic compound, they have carbon atom. Maybe amine, you unmute. Maybe you answer this question. During bonding in organic compounds, we can't talk about bonding and we don't talk about a carbon atom. Now, Ami.
Excuse me, sir. Yes, sir.
Yes.
Sir, my question, first of all, was in the other previous part of ozonolysis.
Yes.
Sir, on that reagent of ozonide and tetrachloromethane, you said something about you can either put warm, but for me, what I heard, it was less than 20 degrees.
Yes.
And then on that part of hydrolysis, there is zinc solid, water, and then for me, I thought instead of putting warm, we're supposed to put ethanoic acid.
No, we can use zinc or ethanoic acid. Auntie, you recall, it is hydrolysis on warming the ozonide or during the hydrolysis with the mixture of, you listen to this, it is the mixture of zinc and water, or, are we there?
Yes.
Zinc and aqueous ethanoic acid. So if you use ethanoic acid, then leave alone water. So it is either zinc and water and warm, or zinc and ethanoic acid. And if you don't want to use, now let me ask you, if you're warming water, can you warm water and you go beyond 100 degrees? Will that one be warming or you're boiling?
No.
You'll be boiling, isn't it?
Yeah.
So when we were warming, we just use little temperature, and that's why we just say warm. But if you commit yourself to temperature and you say less than this, it is still okay. I'm not saying that that is not nice. But if you say warm, you're still in a better position. Now, maybe to ask you a question before. Yes?
Because teacher, for me, whenever I could be synthesizing, I could always use that hydrolysis step. I could always use zinc, water, then I also add the ethanoic acid. I thought they go three in a row.
No. It is either zinc and water or zinc and aqueous ethanoic acid. You don't need to put all of them. You can you can also check in those other textbooks you have used, you have ever used.
Okay, thank you, sir.
Maybe to ask you a small question. What's the maximum number of bonds a carbon atom can accommodate?
There are 4.
There are 4. Very good. Okay. We are diving into bonding. Can you read for me the first paragraph there?
For me?
Yes. And then Grace. Grace, you have disappeared. Yeah, Grace has disappeared. Your hand was up, Grace, but you read for us. Maybe another person will answer that question after. Read.
The first paragraph.
All those ones there.
Carbon can form a maximum of 4 bonds in all its compounds, which may be single or multiple.
Good.
Bonding in organic compounds is covalent, and it involves hybridization in different atomic orbitals or atoms involved.
Any question on that? I believe it is.
What is hybridization?
Okay, good. Thank you very much. Let's hear. You can mute, and then Lot can answer for us what hybridization is. Yes, Ruth.
Okay, hybridization is a mixing of orbitals in an atom.
Mixing of
orbitals in an atom.
In an atom.
In the excited state.
In an excited. Are you telling me that even atoms become excited? Excited state? Uh-huh.
To form degenerate orbitals.
To form what?
Degenerate orbitals or hybrid orbitals.
Use those simple ones. Hybrid orbitals. You want us to run away? Ruth. You want us to run away with degenerate. Okay, so to form hybrid orbitals. What do you know about hybrid orbitals?
They are orbitals of the same energy.
Okay.
And
yeah,
basically.
I like that. Maybe to continue to ask about this. You say it is mixing of orbitals. What are atomic orbitals?
This is a space where it's a space where an electron can exist.
Okay.
I don't remember the definition properly. That's what I.
But that is nice. I think they should first clap hands for you because you gave us very good definition and you know actually what you are talking about. You know what atomic orbitals are. You know what hybrid orbitals are. Maybe now, just take us through this next slide. Take us through that whole slide. And if there is any question, they are going to ask you because I've seen that you're good there now. So if she's going to read for us that part, if you have a question, ask Loth. Loth is going to respond. And if you have any question on hybridization, please ask today. I'm going to take you through the first one. The remaining ones will be yours to try out. Okay, Loth, continue.
So hybridization is the mixing up of atomic orbitals, resulting into the formation of new hybrid orbitals that are ready for bonding. Before hybridization takes place, excitation first occurs. For example, carbon is excited as shown below.
As shown below. Hey, but first wait, they said as shown below. Can you do you think you can take us through how carbon becomes excited?
Okay, it's when heat energy is supplied to a carbon atom in its ground state. Okay, it's in its normal state. One of the s electrons, like since its electronic configuration is 1s2, 2s2, and 2p2. So one of its electrons.
We move slowly. 1s2, 2s2, and
2p2.
2p2. Okay.
So when heat energy is supplied, one of the s electrons is promoted to the 2p orbital of higher energy because
which s electron? Which s? Because I'm seeing 1s and 2s.
The 2s electron.
Why 2s not 1s?
Because I don't remember the reason teacher gave. Let me see.
Okay.
I don't remember.
But it is the closeness. If you look at 1 and 2, 2s is close to 2p compared to s, yeah?
1s.
Now, before you continue, allow me to show the ground state of carbon atom because you told me last that we have the s orbital, 2s orbital, and then we have the 2p orbital. And in the 2s orbital, there are how many electrons? We have two. We have 2. And then in the p orbital is divided into 3. And can accommodate a maximum of 6. 6. So which means if we have 2, we can distribute the 2, 1, and then 2. So this one, you're calling it the ground state. The ground state. Please, those people, they should be writing down those ones who are seeing this for the first time, or they will follow the video maybe later, but it's better when you note down. Okay, continue.
So we said heat energy is applied to the carbon atom in ground state. And then after that happens, one of the s electrons is promoted to the 2p orbital of higher energy. Why? Because there is a, how did she say it? There is a, that orbital is having a free, yes, it has a free partition.
Yes, this
That
free
free
area.
part. Yes. So it's that fully filled 2s electron or 2s orbital releases one, and that one enters into that space in the p orbital. So when that happens, the carbon atom is now said to be excited.
It is said to be excited, which means that process, when it is moving from this side, occupying this free orbital, we call that one the excitation.
Yes.
So during excitation, that's when now this one says, there is a free bed in the other room. Oh, now if there is a free bed in the other room, in senior 3, maybe this one is senior 2, and the next dorm is senior 3, and that they are sleeping 2 people on one bed. So they hear that, hey, there is a free bed in senior 3 dormitory. So this person in senior 2 says, oh, if there's a free bed, kanziruke huyo, I go and sleep that side on that free bed. So that is the excitation. They become excited, and then they go to another level. So which means at the end of it all, the s orbital is going to remain with only one electron, isn't it?
Yes.
So this is S, and then now this one, it has this is 2, which means now maybe it's better to use a different color so that we see them. This one is 1, this is 2nd, and then here we have the 3rd. I think that is more clear. And you're telling us that now here carbon is said to be in excited state. I think that is enough.
Then what happens? Okay, I think we'll first stop to the basic parts of hybridization, because if I continue, it's like I'm talking about SP3.
Okay, thank you. Yeah, I think now there you have told us how it becomes excited. Now, when it is excited, that's when it can be free to bond with other when it is in excited state. Now it can be able to bond with other elements which are present. Like now, when you go to SP3 or in alkanes, there is carbon and hydrogen. Are you seeing that? So carbon does not undergo the orbitals don't start now mixing with these other ones again. They don't combine with the other ones when it is not yet in its excited state. It does that in its excited state. And Ruth has been able to take us through how the excitation takes place. Here is the definition that we are trying to tell us about an atomic orbital. Maybe you can read it and then we move on.
Okay, an atomic orbital is a region of space around the nucleus of an atom where there is a high probability, but not of absolute certainty, of finding an electron of a given energy.
I believe that's what you told us, yeah?
Yes.
Yeah, okay, good. Now, this one, it leads us to different types of hybridization. How many types of hybridization do you know? Carbon undergoes 3 types, isn't it? There are 3 types it undergoes. Can you list some of them? How many? There are 3. Number 1, number 2, and number 3. Number 1, okay, no. Let me have another person. Who is ready? Samsung. Okay, Ruth, thank you very much. Can we clap hands for Ruth because she has led us very well? Let's clap hands for her. But these people, okay, good. Okay, Samsung. Okay, thank you.
Master, just for me, I had a question about hybridization because
Ruth, come back. Ruth, come back. Ruth. Ruth,
For sure, I'm
put up
getting
the. You're having an issue. I want Ruth to answer because she has led us well. Ruth, Ruth, unmute. Okay, ask.
Yes, please.
They have a
My
question
question.
for
Yeah, it is all about hybridization, everything about hybridization.
you.
Mm.
No, have you understood this introduction of what hybridization is?
No, actually, I've been off. That had gone off, so I've loaded some.
Oh, sorry. But we have not moved very far. Maybe, Ruth, just in a minute, take him through. Take him through, and all other people maybe were somehow lost, and then we'll move on faster. Ruth?
Okay, I'm going to summarize.
Yeah,
But
in 1
the
minute, actually.
hybridization is just basically mixing of orbitals in an atom to the excited state so as to form hybrid orbitals. For you to understand it better is that before a carbon atom bonds to any other element, especially hydrogen or any other element, it must first be excited. And what we mean by excitation, as you see on the screen, is that when it's heat being supplied to the carbon atom in its normal state, what we call the ground state, then one of the s electrons, if you remember the electronic configuration of carbon, it's there written. So one of the s electrons in that 2s like the 2s orbital, it, let me call it, jumps, or it's promoted to the 2p orbital, that space where you see it as arrow. So the 2p orbital, what higher energy, and we said it's the electron of 2s that jumps or is promoted to the 2p because like it's in close proximity to the 2p. We cannot have an electron of 1s jump direct to the 2p orbital. Then we also talked about, after that has happened, whatever I've just said, the heat energy causing an s electron from that 2s orbital to be promoted to 2p, that's all called just excitation. After that happens, it's what we are going to see under the types, whereby the 2s attaches to the that p orbital to become a SP3 or SP2 or SP hybrid. We are going to see that. So then we also had to understand an atomic orbital, what exactly it is. It's a space around the nucleus of an atom where there is a high probability of finding an electron. Yeah, and this knowledge helps us understand how carbon, a non-metal, is able to bond with other elements, especially as a central atom.
Thank you. Yes, I have understood. Thank you,
Okay,
sir.
so,
Thank you.
okay. Thank you, Ruth. Yeah, I think that was a good explanation. And now we are here on the types, and someone wanted us to tell us the types. Samsung. Oh, Samsung, you had a question we have answered. Now, Imlan.
Yes, teacher.
Let's list them very fast. Number one.
We have SP3 hybridization.
SP3 hybridization. Okay.
Then SP2 hybridization.
SP2 hybridization.
And SP hybridization.
And SP hybridization. Which one are you going to take us through? And of course, because of time, you're going to use only 5 minutes. And because of time, the remaining ones will be for the members to practice. So which one? Maybe you can take us through the first one. Yeah.
Okay, sir. Let me
take us through the first one.
When we look at SP3 hybridization, mainly we are talking about the sigma bond, and a sigma bond is a single covalent bond formed by overlapping of the S and P orbitals. As you
Okay.
can see on the screen, they are saying that it occurs when one s atomic orbital combines with a 3p atomic orbital, resulting into the formation of 4 hybrid orbitals that are tetrahedrally arranged on a carbon atom. So we know the electronic configuration of carbon, which is 1s2, 2s2, and 2p2. And the previous speaker talked about excitation of this carbon atom, whereby the electron will go into another, how can I call it, orbital, or okay, it is excited to move into the other. Okay, that.
This one.
Now, when
So
we open up our hydrogen, pardon?
I was trying to bring illustration of here so we have our excited state of carbon, isn't it?
Yes.
And we are seeing that in a excited state, the P is now having 3 electrons, yet initially it had 1, and where the 1 is coming from is the one which moved from the 2s to 2p and occupied this free space. So in excited state, we have this these electrons. In S we have 1, and in P we have 3. Now when you come to hybridization, the SP3, actually I think whenever we talk about SP3, there is S combining with P, but it is 1s combined with 3p. This three, this superscript is indicating that actually in P we are using 3 of the P's. Are you seeing? When you go to SP2, which means we're using 2 of the P's. When you go to SP, we're using 1 of S and 1 of the P. And when you talk about the SC, S is from where and P is from where? By the way, that is something that we need to understand. Is SC, are we talking about this S? Are we talking about is S and this P? What are we talking about exactly? Okay, Imlan, please move on. I'm trying to show the illustration. So from the definition, you're telling us that it is 1 s orbital. Maybe I rewrite it here. So you're having s orbital. We have 1 electron for S, and then we have 3 electrons for P, isn't it?
Yes.
Please implant. Then we are forming. We are forming how many? How many are we forming? Are they all going to be combined?
No.
What do we form?
We are going to, because we are going to bond it with a hydrogen atom. And you are going to bring
and now that one is going to come in when you're looking at example. But now we are looking at generally. What is SP3 hybridization? You get? So Imlan, from the definition, isn't it? You have told us that this occurs when 1s, this is 1s orbital combined with 3p atomic orbitals, resulting into formation of 4 hybrid orbitals. So which means our product is 4sp3, the 4 hybrid orbitals, and now they are having the 4 electrons. Are you seeing that?
Yes.
But this can be exhibited in alkanes. Are we there?
Yes.
And that's when you're now going to take us through this example of methane and are going the 4 sp3 hybrid orbitals of how they come about. Yeah?
Yes.
Okay, now take us through that. If you have a question, please raise the hand as he's taking us through the hybridization of methane, sp3, how the methane undergoes the sp3 hybridization. So what happens?
So under SP3 hybridization, we are seeing an example of methane and hydrogen. So the 4 sp3 hybrid orbitals of carbon are going to overlap with the 4 s orbitals or 4 hydrogen orbitals that are going to whereby when they overlap, they'll be forming a sigma bond between the carbon and the hydrogen. So when we bring our hydrogen atom, each is going to bring in one electron bonding into each of the sp3 hybrid orbitals. An electron will be added into each of those, how can I call them?
Okay, yeah, I've got you. Actually, you have told us that in methane, the 4sp3 hybrid orbitals. Where are we getting the 4sp3? We have seen from up there, the 4sp3, these are for the carbon. Are we there? For carbon.
Yes.
But you recall methane as methane. Maybe when you talk about methane, we are talking about this methane of CH4, how it comes about. So it has a carbon and hydrogen. So it's telling us that the 4sp3 hybrid orbitals of carbon, of this carbon, they overlap with 4s orbitals of 4 hydrogen orbitals. So which means for hydrogen, for it has only one electron, that's why it has only s. Are we seeing that? So when you come to carbon, so which means you can represent this by showing us our carbon. You recall that they say that they are tetrahedrally arranged. Do you recall this? Tetrahedrally arranged on carbon atom. So we're going to showcase that the 4sp3 of carbon, they are tetrahedrally arranged. So you can have them, just this one is the first one, tetrahedrally arranged. We have another one. Then this one can be, of course, the 3D, yeah? It may not look very nice, but I believe it is nice, somehow nice. Maybe I put, it is one electron. They all have only one. So these are orbitals of carbon, which are the 4sp3 orbitals of carbon, which are tetrahedrally arranged, and they are combining with 4 hydrogen atoms. 4 hydrogen atoms, but you recall that every hydrogen atom, it has one s. That's why we are seeing that the 4s orbitals. So which means that every hydrogen atom has one orbital, which is now going to combine with these ones. And when they combine, we are going to have this carbon. You recall it had these ones, which are tetrahedrally arranged. We had there only one electron, one electron, one electron. So when you bring the s orbital of hydrogen, it is going to come, the first one will come and bond with this one to form a bond. Even this one will come and bond with, bond with this one. This is another hydrogen. They form a bond because it's coming with an electron. Even this one will come to form another one. And even this one will come to form another one. And the end of it all, this one can also be represented as, or C, because when you see 2 electrons, that is a bond formed. When these 2 electrons, that is another bond formed. That's where this structure comes from. The hydrogen, this indicating this one, the other one, this one, and the other one. Or which you can also write as CH4. Imran, do you think we need to explain more, or that one becomes clear?
I think that is enough. Maybe what they need to know about is the bond formed in between.
Yeah, I like that. Which bond is formed?
The bond is called the sigma bond.
So the bond formed is the one we call the sigma bond. Why do we call it sigma bond?
Well, it is called a sigma bond because it is formed by overlap of this s orbital of the hydrogen and the p orbitals of the carbon.
So it is due to the head-on overlap between the other one, the s orbital, and the one for carbon. So there is head-on overlap that is forming. And how many sigma bonds are we forming here?
We are forming 4 sigma bonds.
So you have 4 sigma bonds. Good. I see it is 4. How many minutes can we add ourselves and we stop? We look at the SP2 and we end, or we end at that? People can go through the remaining ones. Can I hear from us? What do we say? Can we add ourselves like 5 minutes, or we can try the remaining ones? Samsung, what are you saying?
Let's finish.
Okay, we finish the second type of hybridization. Then the third one will be for you guys. Maybe let me take us through very fast. Samsung, read for us. SP2 hybridization.
SP2 hybridization. This occurs when one s atomic orbital combines with two p atomic orbitals, resulting into a formation of a three SP2 hybridized orbitals that are arranged in a triangular planar shape. The unhybridized orbital is at right angles to the hybridized orbitals.
Sorry about that. I think I was speaking when you guys are not listening. But maybe what I want to do is to illustrate, and then you take us through the example, isn't it? So here you're telling us that it is 1s. Now it is 1 electron for s, which is combining with 2. But now you recall this p, it had, okay, let's put the excited state. The excited state of carbon is like that, isn't it? But in SP2 hybridization, it is 1s, which is combining with 2p. When you say 2p, there are 2 orbitals of p and 1 orbital of s. 1 electron for s and 2 electrons for p orbital. Are we there? And they are saying that when they combine, they form 3 hybridized orbitals. So the 3 hybridized orbitals. Now, 1 is for s and the 2 are for p. And now they are forming what we call the 3 SP2. But you recall there is 1 for p which has not been touched, and therefore that one remains alone. And this is the one we say that is unhybridized. It is unhybridized. And these 3 are the ones which are hybridized. Are we there?
Yes.
Now they say that the unhybridized orbital is arranged at right angle to the hybridized, while the hybridized ones, they are 3, they arrange themselves in a triangular planar shape. Maybe what we need to show is a triangular planar. A triangle, I believe you know that a triangle is like this, isn't it? So when you say a triangular planar is something which is like a triangle. So we are going to have a carbon. I want to start with the hybridized orbitals. You recall they are how many? 3. And they are arranged in what? A triangular planar. So since it is a triangular planar, you see, we have 1 on that side, another one. These are 2. And then we have the third one. Are you seeing? That is a triangular planar. I believe you're trying to see that. Now, because we have this triangular planar, we still have another orbital for this carbon. But this other orbital is unhybridized. It is this one which is unhybridized, and they say that is at right angle. So at right angle, we can arrange it here very well. For it, we can use another shape, maybe triangular. Half. Just this is one orbital, but half on down and half above. Just know it is one orbital, but which I'm showing on both sides, because we're looking at 3-dimension, but I may not show it very well here. Yeah. Don't forget that we're looking at ethene, and ethene is C2H4. Are we there? Hello?
Yes.
Please, we are together. Make sure that you're speaking. That's when I will know
Yes.
that we are moving together. So you have 2 carbon atoms, which means even the second carbon atom is undergoing the same. Are we there? So it is going to
Yes.
undergo the same. So you have another carbon atom also arranged in having the 3 orbitals arranged in triangular planar. So this one is going to come. But when this one comes, it will meet this one. They bond. They form a bond. Have you seen how the other bond comes about?
Oh.
Then you recall they still have a pi, the unhybridized. So the unhybridized will still be arranged at right angle to these ones. This is half down and half up. So what happens? These ones, you call these ones have already formed a bond. These ones. Now let me use another color. We have 4 hydrogen atoms, and so these unhybridized orbitals, for them, they undergo what you call sideways overlap. Sideways overlap. So this one, it overlaps with the other one. And even this one, it overlaps with the other one. Maybe let me use 2 alone like this. It overlaps with this one. It should be 1, but as I said, it is half-half. So which means, and when they overlap, they form what you call a pi bond. But you call this is half of the other one. So this one becomes a half of the pi bond, and this one forms a half of the pi bond. That's why they form a full bond, which is called a pi bond. Then these other orbitals are the ones which overlap with hydrogen atoms. You recall this one, they have 1 electron, even this one has an electron, even this one has an electron, even this one has an electron. I want to use another color so that you can see very well. So this one will be for the hydrogen. So hydrogen is going to come with its electron, they form a bond. Hydrogen will come with its electron, they form another bond. Hydrogen will come with its electron, they form another bond. Hydrogen will come with its electron, they form another bond. So finally, we shall be having, look at this. Let me use another color for clear, but will this one be clear? Maybe green. Now look at this. We're having this carbon here. We're having this other carbon here. But now, there is a bond between this carbon and this carbon due to this head-on overlap. There is this one. Then there is the other one, which was formed due to the sideways overlap, the pi bond. I'm showing it with the blue color. Okay. Now there is the one which is formed between the hydrogens. So there is a hydrogen atom here. There is hydrogen atom here. There is hydrogen atom here. And there is a hydrogen atom here. And that is the one we call ethene. Are you seeing how ethene has come up?
Yes.
Now, we can even now count how many sigma bonds do we have? How many pi bonds do we have? These are sigma bonds, and then these are the pi bonds. How many pi bonds do you see there?
There's 1 pi bond.
There is 1. How many sigma bonds?
There are 4.
Are they 4?
Yes.
There's another one which is formed due to head-on here. There's the one which is formed between hydrogens. There are these ones between hydrogens, but also there's this one, the blue,
they're 5.
the green. So they are now 5.
5.
So it has 5 sigma bonds and 1 pi bond. Okay, I believe that was clear. I boiled
Yes, ma'am.
only 5 minutes, but I can see they have gone beyond 5. Imran, are you still there? As I
Yes,
disappear also.
teacher.
Yes?
Yes, teacher.
I believe now the SP can be done. I've just done this for us, but I'm going to share this document. They'll be able to share it, and then you can feed in. You can show us that, and then you also try that one for that example. Then there is a question here. What are some of the differences between a sigma bond and a pi bond? Of course, because of time, I can't go beyond. But the answers are there. But also, I believe you also have your responses. But time is a key. We have to manage time very well. This is just a reminder that our next lesson we shall be looking at we shall be looking at physical chemistry. We shall be looking at physical chemistry, and
So
yes.
which topic? Which topic?
Which topic? We shall put polls in the group, and we shall be able to see whether we should start a new topic for senior 6, or there is a topic in senior 5 that would like us to talk about. Maybe let's put in the chat. Put in the chat which topic in physical chemistry. Should we go to the first topic of senior 6, or there's a topic you think we can look at? So we can share. Otherwise, this marks the end of today's lesson and end of our discussion for organic chemistry. I know we shall be meeting in different facilitation and other lessons which they organize in the upcoming holiday, and because other days I want us to look at physical chemistry. But as I said, thank you very much for your attendance, and let's keep on enjoying the beauty of chemistry. It starts by liking the subject and then you pass it. So that's why I normally tell students that enjoy the beauty of chemistry.
So we do physical equilibrium.
Yes?
Do physical equilibrium.
Physical. I'm seeing someone saying chemical equilibrium, someone saying colligative properties. That is the one for senior 6, okay? Someone is saying physical equilibrium, someone is saying first topic, another one is saying thermochemistry, equilibrium. So equilibrium is common for many people. It's okay.
Yes.
So next time we shall look at our first topic for physical chemistry. But what I'm going to do is to give you highlights and key points so that when you go to school and you're studying it, it is just like revising. So what you do, go and read the first topic of senior 6. The good thing, Mr. Kaziba shared with us the syllabus books. So we do research so that when we meet, you already have a clue and we are just discussing. I believe that one is clear.
Thank you, sir.
Yeah, otherwise, I want to wish you the best. It has been a very good interactive session. I want to wish you the best. Let's meet another time. Have a blessed
Thank
time.
you, sir.
Please lead us in a closing prayer as we stop. Imran.
Yes, teacher.
Closing prayer.
All right, let us humble ourselves for the prayer. Oh, dear Jesus Christ, we want to thank you for today. We want to thank you for everything that you have done for us. We thank you for our great teacher who has taught us chemistry and the knowledge that you have brought into our minds. And we pray that we might continue to understand chemistry, that it might continue to be a simpler subject to us who are over it and to others, Lord. We pray that we might enjoy it and we might continue to pass it, Lord. We pray that you might continue to protect us and protect our teacher also, that you might embrace us with knowledge and grace to conquer more into this world. In the mighty name of Jesus Christ, we pray. Amen.
Thank you. Have a blessed time.
Thank you, sir.